Hola. Sí. So, good afternoon, everybody. I'm going to start this session about the future developments in technology, services, and internet architectures. So we are going to start with our the first speaker. He is Bruno Cuotin. Cuotin, sorry. He's a research fellow in the IP networking lab at the Université Catholique de Leuven in Belgium. So please.
So good afternoon. Yes, I will need. Thank you. So the talk I will present is not only my work, but also the work of Luigi Iannone and Cédric Delaunoy, Sébastien Barret, and Olivier Bonaventure, all from the IP networking lab at my university. So the talk I will give here will focus on two solutions we are working on, and in the framework on developing future internet architecture. So first, I will describe a few issues we have with the current internet architecture, mainly the growth of the routing table, the number of BGP messages exchanged into the internet, and the lack of route diversity and control on the forwarding path in the internet. So I think you all know this graph, which shows the history of the number of prefixes you can see in the BGP routing tables. And you can see that at one time, the introduction of CIDR has reduced the growth of the routing tables, but now the growth is still exponential. So you can see that the number of prefixes, how does it work? I don't know. Do you see something? No, okay. Okay, thank you. So, you can see that the growth of prefixes is quite sharp, and we have reached more than 265,000 different prefixes in our BGP routing table today. And it's not only due to the arrival of new players, but also to different practices that related to the use of BGP, multi-homing, so you connect to different providers, traffic engineering, when you advertise different prefixes through different providers with different path attributes. Another problem of the current architecture is the number of BGP messages you can receive. So here is just a snapshot of the number of BGP prefix changes, so prefixes that are updated or withdrawn on a single BGP session. You can see that there are periods where you get more than 100 BGP messages per second, which is a lot. So the question is, do you need all these updates, since they might not be related to destinations you are interested in? Third issue, the lack of control on the BGP path. So BGP is a path vector protocol, so when one router receives two routes towards the same prefix, it will only advertise a single route to its neighbors. So it reduces the route diversity. This has an impact on the number of different paths you can see from one network to another. So here you can see that ASY receives two different routes from ASX, but they both enter through ISP-A, while ASX probably also sends routing information through ISP-B, but they do not arrive to ASY or they are not selected. So, but if you have a look at the different combinations of ISPs, you can imagine that we could have 4 different paths between these 4 ISPs. So one solution that is envisioned at this time is named locator identifier separation, and I will tell a bit more about it in a few minutes. Based on this locator ID separation, I will then present 2 different solutions, one which is router-based and which is called Lisp, and the other one which is host-based, and it is called Shim6. So let's start with the locator identifier separation. So the idea is that IP addresses have 2 different functions. One is the identifier. They identify uniquely a network interface. And the second role is the role of a locator, where the IP address is used to know how to reach the network interface. So both functions are joined at this time, and the idea is to separate both functions, and we will see what is the advantage. So here is a first advantage. You can, by separating the different spaces, identifier and locator, you can increase the path diversity inside the internet. So the experiment here is based on data from the RoadViews project from University of Oregon. And we have had a look at all the different BGP peers that were sending their BGP routes to RoadViews. We looked at the number of different paths available between pairs of these peers. So most of these peers are multi-homed, and we looked at the number of paths available with BGP. And we saw that with BGP, with dual-homed stubs, you only have at most 2 different paths towards each destination. That's only because BGP is path vector protocol. While if you separate the locator and identifier, you can use the destination, the two or more destination providers to reach the destination. And with that, you increase significantly the number of available paths. So a basic rule of thumb to know the number of paths you will have with the destination is the number of provider you have times the number of provider of destination. And you can see that for most of the destination, you already have an increase, a significant increase of the number of different paths. Second problem is that if we have more path diversity, all these paths do not have the same quality. So we did a second experiment based on the RIPE TTM data. So RIPE TTM test boxes are placed all around the world, and they perform one-way delay measurement between each other. And we grouped some of these test boxes that are located at the same geographical position into the same virtual AS, and we looked at all the different paths between all our virtual ASs and what is the latency along all these different paths. You can see on the graph here, so these are all the pairs of the virtual ASs, the delay on all the different paths between one pair. So here, these are all delays along the different paths between 2 virtual ASs. And you can see that there is a lot of variation. You can have paths which only have 250 milliseconds, and paths that are 400 milliseconds. So it is important to select the right path. If you only use BGP, the path that is used is based on metrics that are completely unrelated to latency. So you could use with BGP the worst path. An additional advantage of the locatorized separation is that you could reduce the number of routing entries inside the routing tables. First, because you won't advertise the identifier space into the default free zone, into the core of the internet. And moreover, it's possible to use new prefix allocation schemes that allows to better aggregate the prefixes. So for instance, if we could allocate to all the stub ASs prefixes that are parts of their provider prefixes, then we could significantly reduce the size of the BGP routing tables. We did experiment with large AS topologies with around 15,000 different ASs, each one advertising one prefix. And we can see that with BGP we would have one fib entry per AS, so 15,000 fib entries. So probably here out of the graph. And with our different schemes, it's possible to reduce significantly the size of the routing tables. So now, what are the two solutions that are discussed at the IETF now? First, Lisp. So Lisp is a protocol proposed by Cisco, and the idea is as follows. So suppose that we have two dual-homed ASs, AX and ASY. They both have two providers. So ISP A and B for AX and ISP J and K for ASY. Inside ASX, addresses of the network interface are taken in the identifier space, and it's the same inside ASY. And these spaces are not advertised by BGP in the default free zone. Instead, only the prefixes of the core, the ISPs and other transit networks are advertised here. So only the locators. So here we have IDs, and we have one border router of ASX that has one IP address in ISP A, that is one locator A of ASX, and another locator for the other border router that belongs to the address space of ISP B. And it's the same for ASY. So ASY has two locator J and locator K. And the simple idea of Lisp is that if one host in ASX has to send a packet to one host Y in ASY, it sends it to one of the border routers, depends on the policy of ASX. Then this packet is encapsulated inside another packet, which is sent towards the locator J. So the outer header destination address is now J inside of Y. And then this packet is sent to the border router of ASY. Then there it is decapsulated and the packet is sent to Y. With this very simple scheme, it's possible to control the path between all the locators. So with that, you can select that one packet from X towards Y will go from A to J, from A to K, from B to J, or from B to K. So you have additional control on the path through the internet that you don't have with BGP. Of course, here I haven't said how the identifiers that are used inside the stub ASs are mapped to the locators. For this, there are currently different solutions that are discussed at the IETF. So some are based, for example, on the DNS. So you would make a DNS request to get all the locators available for a destination identifier. There are other techniques such as using distributed HTTPs over the networks and so on. But in this talk, I will only focus on DNS type mapping systems. We have done some measurement based on the traffic that goes out from our university network. So we captured net flow statistics, and we simulated the size of the cache, the mapping cache that would be needed to forward this traffic. So each time a packet goes out from our network, we need to find its destination locators, and this is a request. When we receive a response, we store that response in our cache. Our cache has different timeouts, and we measure the number of entries we'll have in the cache by using this different timeouts. So you can see that if you use a 5-hour timeout, your cache size can grow very large. So 100,000 entries, it's becoming close to the size of the BGP routing table. So not much advantage. But if you have shorter timeouts, then you can have a significant benefit. Second experiment is that we compared the number of mapping lookups that are required by using here in this case the green timeout, so the 30-minute timeout, and you can see that compared to the number of DNS lookups that are performed by our network, the number of DNS lookups needed for the mapping is much lower. So we have a Lisp implementation available freely in our university. It's developed by Luigi Giannone, and if you are interested in testing it, you can get it from this website. So now that I've talked about router-based solution, there are also host-based solution, and here I will only talk about Shim6. So Shim6 is in the framework of IPv6. So in IPv6, the multi-homing is a bit different from IPv4, as if you multi-home, you won't need necessarily an AS number, but you will receive portions of the prefixes of your providers, and each interface in your network will have an IP address in both prefixes. But this poses problem for the survival of TCP connections. So here, for example, if we have a dual-homed stub here that has a TCP connection with another host here, so the destination used here is the source address used here is an IP address which belongs to the prefix of the blue provider here, and the destination in red belongs to the red provider of the destination. Now, if there is a failure and packets cannot be sent through AS2, we cannot send the traffic through the other provider. Because first, there could be filters that deny the forwarding of packets where the source address is not in the prefix of the ISP, the green ISP. Second problem is that if the packet reaches the destination, it will not correspond to an existing TCP context. So at the TCP level, it won't recognize the packets coming from a source address inside AS1 because the initial flow was with a source address in the blue network. So Shim6 allows to solve that problem. Okay. So Shim6 is just a small sublayer which is in the IPv6 layer, and that allows to map the transport level identifiers to the locators, which are the interface, the network interface addresses. And when you have Shim6, the same scenario as before becomes as follows. In addition to the source and destination addresses, each TCP connection or each flow can be associated to a context tag, which is negotiated. And afterwards, if there is a failure, the diverted flow will use as source address an address in the AS1 prefix, and with a context tag in the IPv6 Shim6 extension, which will allow the mapping to the IP address which was used as identifier by the transport layer, and that without any change in the application programming interface. So you can, all the applications using the socket API will still continue to use without any change. And we also have in our lab an implementation of Shim6, which is available for the Linux kernel. So again, if you're interested, please visit our lab website. So as a conclusion, the separation of locator and identifier can allow to reduce the routing table size growth. It can reduce the churn, and it can allow to have more path diversity and more control on the path. So here I have presented two different solutions, one router-based and one host-based. We have implementations. If you want to try them, please go to our website. And if you have questions, I'll be happy to answer.
So, are there any questions to Bruno? No? Seems no. Okay, thank you very much. Our next speaker is Our next speaker is Klaus Ravi from Adva company. He's just a moment. Klaus is a principal networking engineer at Adva AG Optical department. So, thank you.
Thanks, Esther, for the introduction. Good afternoon, everybody. Happy to speak here again. Last year was an update on 40 gig, so I will cover 40 gig today only with one or two slides. I should mention that this talk was partly produced by my colleagues Jörg Peter Elbers and Michael Eiselt. So this is the outline. As I said, 1 or 2 slides on 40 gig. Then the major part of the presentation on 100 gigabit transport. And we, as ADVA Optical Networking, are really referring to transport here. So we are a transport company, WDM transport, optical transport. And there is enough problems with optical transport when it comes to 100 gigabit per second per wavelength over larger distances. So 2 further parts on 100 gig, status and requirements, and then something on technological solutions, modulation, physics, stuff like that. So this is the scenario that we face when talking about 40 and 100 gigabit, and that means 40 gigabit Ethernet and 100 gigabit Ethernet. We have clients, transport equipment, and a transport cloud. And hence we have at least 2 different types of interfaces, and hopefully it is exactly 2, not 3 or more. What we call client interface and a line interface, or maybe a remote interface, WDM interface, whatever you call it. And then there are various standardization bodies who are dealing with these interfaces, and that's mainly IEEE.3BA task force for the client interface. That is the LAN interface. And then it's more the ITU, study group 15, that is dealing with the wide area stuff. And that, well, I will show on some slides. And regarding transport, we are talking reach extensions into the megameter range, potentially thousands of kilometers, of multiples of 100 gigabit per second. And regarding total capacity, of course, we are talking today multiple terabit per second, because everybody agrees this seems to be necessary to carry at least 5 or so terabit per second per fiber pair in the very near future. So this is our scenario. This is one of the 2 slides on 40 gig. The situation as of today, well, 40 gig came from, or was massively pushed by the server community, and it may go to a certain extent into networking, telco networking as well. And there is a certain question mark. Yes, we do see mass rollout today with AT&T, for example, but many carriers and many people are waiting for 100 gigabit and would like to skip 40 gig. So it's a little bit unclear. My guess is it will come as a transport technology massively. Nonetheless, even if it's pushed by server and computing community, there is what we call OTN, Optical Transport Network. That's a standard, an ITU standard. Framing necessary because, for example, for interworking, if different such clouds have to interwork, that must be standardized, and that would be the OTN. I will come back to OTN with 100 gig. The good thing is 40 gig is more or less established. There is mass rollout. There is applications, 40 gig interfaces at core routers, for example. There is a mature components base, which is pretty relevant. So yes, we can now get components, and various standards exist. So all of this is good. It can be rolled out. However, and that may become a problem, there are lots of different transport solutions, and these refer to different modulation formats. Like we can see here, this is not necessarily complete, but it is the relevant technologies, and this now is really modulation and physics, that you can get as products today. You can't, 40 gig and 100 gig, you can't transport using the same or a similar technology than we did with 10 gigabit. 10 gigabit was light on, light off for logical ones and logical zeros. This does not work anymore with 40 and even less with 100 gigabit. So we are now back into the space of strange modulation schemes, like the reinvention of duo binary, like CSRZ or CSRZ, which is a certain pulse coding or pulse shaping scheme, and then the various flavors of phase modulation, phase shift keying. The good thing is solutions exist. The bad thing is they all have different pros and cons, and this matrix may differ a little bit if other people would prepare them. But the problem is you can't get a single solution that covers all applications, either long distance with, for example, massively high allowance of chromatic dispersion and polarization mode dispersion, which are two of the physically constraining effects in fiber transport. And on the other hand, for example, where is it? Good upgradability of existing 10 gigabit systems on every sort of fiber. So there are also certain problems, which I think I indicated last year already. So the message is you have to be a little bit careful when choosing the correct 40 gig technology for your networks. And this will get worse with 100 gig, no matter what we try to do. So now 100 gig, 100 gigabit Ethernet. Situation, it seems 100 gigabit Ethernet now is, unlike 40 gig, is really massively driven by the telco and transport, core networks and whatever community. Maybe it will go into the computing and server area later. And again, in any case, OTN, G709, compliance and standards-based networking and transport will be necessary for reach extensions, for interworking, etc. And of course, unlike 40 gig, 100 gigabit is not established yet. We don't have a stable components market. We are desperately looking for components. It's not even clear will these components run on 28 gigahertz or 56 gigahertz or 40 something. There is discussions regarding the OTN standard. There is, of course, lots of discussions regarding modulation schemes. And then there's these two standardization bodies who, well, have to deal with it. And this is a slide on their focus. As I already said, IEEE will deal on the client interface. That is the, where is it? The LAN interface, short reach or very short reach, parallel copper, parallel fiber, possibly in the beginning no serial fiber, with very aggressive price expectations. And ITU does the long haul part, so mainly regarding OTN, optical transport network, according to G709 standardization, reach, long reach, ultra long reach, single mode fibers exclusively, WDM for multiple channels, of course, likely an accumulated bit rate of 112, but that's not sure by now. So that would be some overhead for the OTN, and with a somewhat relaxed price expectation. And hopefully these two bodies are really properly cooperating. Because if not, we end up with the mess we have at 10 gigabit Ethernet. We have 7 different mapping options for 10 gigabit Ethernet into OTH. Mainly based on the LAN PHY, but then there is this WAN PHY as well. And there's a very clear goal: no dedicated WAN PHY for 40 and 100 gig whatsoever. Some of the ITU objectives, just to explain, a little bit on the OTN. It has lots to do with framing. For example, to provide a forward error correction, that's coding, to reduce the signal noise ratio requirements, but also to provide various overheads in various layers of the OTN. And all of these overheads add useful functionality, management channels, performance monitoring, adaptation of the client payload, and many more useful things. And in the end, there will be a new hierarchy layer in OTN, which will be called, where is it? The OTU4, ODU4, OPU4, which are the different layers, and which will contain the 100 gigabit Ethernet, which will likely have an accumulated bit rate of 112, maybe 120 gigabit per second. And it has, and study group 15 also has to deal with various other mappings, for example, multiples of 10 gigabit Ethernet, multiples of the lower hierarchy layers, that is OTU 3 and 2, and maybe even also other protocols. There is discussions whether or not 10 gigabit fiber channel should be considered, maybe if 10 gigabit InfiniBand should be considered, stuff like that. And this is the likely outcome of standardizations. So again, left-hand side is the IEEE side, and they will go for various interface standards, either 10 by 10 gigabit per second on copper and multimode fiber, or 4 by 25 on, what is it, single mode fiber in with some WDM flavor, maybe widely spaced WDM or so. And on the other hand, and it is pretty unlikely that there will be a serialized version in the beginning. There are many people who are requiring a serialized version. Reasons could be more compact, in the end cheaper, less power consumption, better adaptation to optical transport, etc. But likely in the beginning there will be no such interface. And then on the other hand, there'll be various modulation schemes, all of which get the OTN framing. And our prediction is there will definitely be different solutions in different distance domains. Say something covering distances up to 300 kilometers, something covering distances 300 to 1,000 or so, and then something that goes ultra long haul, even with 100 channels of 100 gigabit Ethernet. And that is clearly for a good reason, and the good reason, of course, is cost. A system that is designed to support 100 channels of 100 gigabit Ethernet over 2,000 kilometers can be expected not to be cost competitive for 200 kilometers or metro applications. And then there is some very severe additional requirements, of course, and that's the right-hand side lower part. Of course, whatever comes out has to be compatible with today's infrastructure. That means with today's 150 gigahertz systems, WDM filters, amplifiers, dispersion compensators, the modulation schemes that are used. And as such, it has to support existing 10 gigabit and the very near future 40 gigabit systems. And this is tricky for some of the modulation schemes. Okay, now for some of the modulation schemes. As I indicated, with 100 gigabit or ultra high-speed transport, everything is getting worse. I don't expect everybody to understand these charts. They should indicate everything is getting worse. That is, the OSNR, the optical signal to noise ratio requirements, of course, increase, which limits distance. The GVD, that is group velocity dispersion or chromatic dispersion, tolerance decreases significantly as compared to 10 gig. And chromatic dispersion, unfortunately, is a characteristic of every fiber. We cannot avoid it. It's simply a characteristic of silica glass. And even worse, polarization mode dispersion, which is more a characteristic of the light waveguide. I mean, the fiber is a light waveguide. Will get dramatically more severe effect, and it will be likely PMD, which will be one of the ultimately limiting characteristics. One word on PMD: a single mode fiber isn't a single mode fiber. A single mode fiber is a dual mode fiber, and PMD means that the two modes that can propagate are propagating at slightly different velocities, and so in the end I get sort of an echo of the faster mode, and this echo causes intersymbol interference and hence bit errors. And then last not least, all the nonlinear effects. The fiber is a nonlinear channel in reality, are getting worse as well. From the one viewpoint, one would try to work at highest power levels because that would give OSNR advantages, higher reach, etc. And then on the other hand, nonlinearity exactly limits power levels. So there is one of the very many trade-offs. And I'm open for lots of detailed discussions offline later. One slide, nonetheless there's hope. One slide on the latest and greatest of OFC 2008, OFC's Optical Fiber Conference, biggest and most relevant in the world, 2 months ago or so. And there were many hero experiments, and in particular one, it's the one with the highlighted number, is really astonishing. They did 164 channels of 112 gigabit per second each over more than 2,500 kilometers. So now it seems, hey, we have the solution. Everything's there. Let's go for it. There is a big but. All these hero experiments are done in so-called recirculating loops, which is lab environment, which is controlled environment. You have controlled temperature. You have no vibrations from wheresoever. And in particular, those with the very high products of accumulated bitrate and distance, they are all right now using sophisticated digital filters, but a digital filter with say 100 or 128 taps running at 100 gigahertz doesn't exist. So it's simply PC-based offline filtering. You send a bit sequence, and then you have days and days for offline filtering. Now, okay, it's not days and days, but it's offline, and maybe it takes minutes or hours. So it is no in-time filtering. So controlled environment, offline post-processing, and that means, and some other limitations as well. Most of these experiments are done at incredibly low power levels. For example, in the range of -3 dBm, which is not realistic. Realistic regional systems tend to run at +3, +4 dBm, which would simply rise the nonlinear effects. Then digital filters are prone to nonlinear effects, and hence that's another trade-off. Message here is there is quite a long way to go still, but hope is there. And this is what do we call it? A block diagram of one of these hero systems. This is coherent optical technology using RZ pulse shaping, that is return to zero, that is pretty good against nonlinearities, using, where is it? Polarization multiplexing, so use both polarization modes independently, make it a real dual mode fiber. and then using quaternary phase shift keying, that is 4-state phase shift keying. And the constellation diagram is shown here. That means I have 4 phase states. So with one symbol, I could code 2 bits. If I transport one symbol, I transport 2 bits of content. And since I have 2 polarization modes, with one complex symbol, I transport 4 bits. And hence the accumulated, the symbol rate or baud rate, as we call it, would be 28 gigabaud, less than actual 40 gig systems. Pretty good, but pretty complex. As you can see, lots of components, modulators, photodiodes, and then this massive digital filter. The 2 diagrams at the bottom of the slide simply say, yes, it works perfect, but again, with offline filtering. And since it is a pretty complex system, yes, we expect it to be able to go for 2,000 plus something kilometers, maybe later even on real-world fiber. But with all these components, which are really expensive components, it'll be a massively expensive solution. Maybe overkill for 200-kilometer metro applications. And that's why we are in a project called 100GET, European project, and developing something else. I'm a bit refusing to call it low-cost 100 gig because there is no low-cost 100 gig. Maybe we should call it lower-cost 100 gig or something like that. Hopefully you realize from the block diagram that it is significantly less complex. If I switch back and you count the number of modulators, for example, and these are complex modulators with 2 input ports each. Then there is 2 complex modulators, and here there's just one single simplex modulator. So that's a reduction by approximately, well, a factor of 4, obviously. And similar thing on the receive end. So this is less complex. It uses less components. It should be cheaper. And on the other hand, this is another weird modulation scheme or constellation diagram. It has 6 states. But if you take a pen and calculate what can be done with 6 states, you end up that you can transport 2.5 bit per symbol. And that would give you, for 112 gigabit per second payload, 44 gigabaud. And now 44 gigabaud is very close to 43 gigabaud. And 43 gigabaud is the standard 40 gig components. So with only very, very slight overclocking these components, which are of course available today, we can directly reuse 40 gig components. So pretty clever. Some nice project partners like Heinrich Hertz Institute in Berlin, Deutsche Telekom, Testbed, etc. And the drawback. That's the diagram here. According to first calculations, it will only support something up to the range of, say, 300 kilometers. And that's exactly what I said earlier. It is cheaper, massively cheaper, potentially, and it will support only limited distance range. There will be different solutions for different distances. And this is by no means complete. This is my final slide. It's just a collection of some of the modulation schemes that are under discussion today. And again, with regard to all the impairments that a fiber transport produces. And again, we see they have, of course, different characteristics. This coherent PolMux QPSK with digital receivers could finally do everything, but again, it's the most complex, and most complex should translate to expensive, and the digital receivers don't exist today. So we have to start with something else. And yeah, here we go. We will develop, or we are on the way developing this 3ASK DPSK, lower cost metro 100 gig. And we are looking, of course, into some other modulation schemes as well. So expect that there will be even 2 different 100 gig transport flavors within a relatively small company like Adva. Okay, with that, I should come to a summary. 100 gigabit, yes, it requires efficient WDM transport. The efficient means spectrally efficient. We have the 50 gigahertz grid today, and transporting 100 gigabit per second in the 50 gigahertz grid means at least 2 bit per second per hertz. This is spectrally efficient. Definitely single wavelength solutions will be required that cooperate or interwork with the existing 2.5, 10 gig and 40 gig systems, and we'll definitely see different solutions for different distance domains. With that, I should be finished. Open for any questions.
So, are there any questions to Klaus? No? No questions?
Nobody understands anything.
Thank you very much. And finally, our third speaker is Marian Garcia. She is the responsible of the operations of the European network Jan2.
All right. Thank you very much for the introduction. Good afternoon, everybody. My name is Marian Garcia, and I work for Dante. I don't know, probably many of you have heard of Dante by now, but in case you haven't, Dante is a company that is in charge of operating the Jan2 network on behalf of the Consortium of National Research Networks. So after the last 2 presentations focusing technologies, I will be talking about operations, operational challenges in providing multi-domain network services. So Jan2 and the Jan2 vision. Well, we have seen for the last few years that there are more and more researchers, astronomers, physicists, radio astronomers that are required to share their resources, their data, their knowledge across the world. In an environment where borders between countries are irrelevant for them, in an environment where cultural differences, technological differences are not relevant for them. They want to have a seamless connectivity. They want to have a connectivity that provides them with high-quality networks, that a connectivity that is tailor-made for their requirements, and of course is an affordable cost. So the Jan2 vision was to provide these services to these researchers. And for that, the Jan2 stakeholders, the Jan2 national research networks, have been working together to provide these services. So yes, so Jan2 is a project that has a vision. Jan2 is not just a network. So how are we getting there? How are we providing these services to these end users? So I decided to go to the Terina Compendium, the 2007. I think there is too many zeros there. But anyway, so to the 2007 Compendium. And I think I found quite interesting information there. It seems clear that there is a trend for NRNs to use dark fiber. They use this dark fiber and they exploit the switching networks and the wave division multiplexing. So we can see a considerable growth in capacity at an affordable cost. And all these NRNs that are becoming to use dark fiber, they own the dark fiber or they lease the dark fiber, can't decide by themselves what type of technology to use. They can't decide based on the technical expectations. They can't decide it based on the cost limitations. So how we found then how to get there is the dark fiber the answer for this vision, or is the dark fiber enabling us to get somewhere? So I decided to do a bit of an analysis. So we have dark fiber. We have NRNs accessing this dark fiber at an affordable cost. And we have, as we said, an increase in capacity. We are able to reach more users. So an NRN or a domain can decide to light their own dark fiber and reach customers that were unreachable using the traditional commercial connectivity. But not only that, if one domain has dark fiber and the neighboring domain has dark fiber, well, we could stitch the dark fiber, and my users could even reach more users in the different domains. So it all is looking good. In addition to that, we said that the dark fiber gives flexibility in technology. And flexibility in technology provides a wider range of services. So yes, so we have dark fiber. We can provide more services, affordable cost, using the technology that I think is more convenient for me. So, well, maybe it wasn't that difficult after all. But if we go a bit farther, what do we have? We have higher capacities. Well, a few years back, when the capacities were not so high, everybody was expecting higher capacity. Now that we provide higher capacity, we can expect the users to require higher performance. Yes, we said we can reach more users, and we can reach more users that are in different domains, but for the first time, it's not only me as a domain taking care of my own infrastructure. It's me relying on other domains' infrastructure so that I can provide services to my users. So I'm looking a bit more complex, and definitely we need a greater degree of multi-domain collaboration. And we said that we have flexibility in technology, wider range of services. Well, with that, it looks like our network complexity is increasing. So, yes, I think we have to increase the operational efforts, and therefore we have to increase the operational cost. So how we really balance these two aspects? We have an affordable dark fiber, but as a consequence, we have an increase in cost in the operational services. So what have we achieved? Where we are in Gen 2? We have hybrid national research networks. We have Gen 2, that is a pan-European hybrid network. So it's meaning that we can provide advanced IP services, but not only that, we can provide pure LandNet and we can provide circuit services. So just to give you an example, Gen 2 is providing these pure wavelengths and GIGI circuits since 2006. These point-to-point connections are crossing Europe and are connecting the national research networks. So in a bit more than a year, we have providing 50 of these connections. So we are dedicating around 300 gigabit per second capacity to big projects like DESA, LHC, Express, and so on. And not only that, is that we are aiming to provide these services across different world regions. So it looks to me that we are at the stage in which we have the technology there, and we need to address the operational costs and the operational issues that derive from using this technology. So I'm not sure if you all will be able to see what is written there, but this was just an example of a connection that was requested to the Gen 2 community. So there were some users in Poland and some users in Canada, and they said, okay, we want a GIGI connection. All the stakeholders, all the domains, put all these connections together, but you have to see we have 5 domains there with different technology using different type of equipment. We go from the National Research Network in Poland, Pioneer, to the Pan-European Research Network Gen 2, to the New York mainland as an internet exchange point, to the National Research Network in Canada, to the end user in Canada. So 5 different domains, 5 different technologies, but what is more important as well is 5 different ways of implementing, managing, and operating the connectivity. So what we learned when we are setting up these connections? First of all, we learned that it's a challenge to set up a connection when each of the domains have their own business model and they have their own way of providing service levels. So how can I promise my customer a service level when I rely in the infrastructure of a different domain that provides different service levels? We learn as well that we had to put extra effort in setting up in a small bit of the connection, but a very important bit of the connection is the interconnection between two different domains. As I said before, it's not just me as a domain trying to set up a connection using my technology and using my resources. It's me trying to make this work with the technology or the resources of the neighboring domain that may be using a completely different technology and maybe using a different approach to provide a service. So yes, another challenge was setting up the connection. So what happens when the connection is set up? Well, we have the next challenge, how we maintain and how we monitor this connection. I mean, up to now, we were using domain control monitoring tools that may not be useful when we are talking about multi-domains, that may not give us the full end-to-end visibility. So important lessons learned, important challenges to overcome. So what do we need? Well, we need multi-domain operations. So several Gen 2 activities have been working and focusing on solving these challenges in supporting these multi-domain operations. The objective from the user point of view is that we'll provide a service that is virtually as one unique domain. So the end user does not care how many domains are in between, how difficult it is for us to set up this connectivity. They only want to have a seamless connection from A to B. But the challenge from our point of view is to deliver what is a complex service packed in a very simple format that has an affordable operational cost. So, as I said before, there are different activities in Gen 2 and outside Gen 2 as well, working in bridging this gap, bridging these operational challenges. I'm not going to talk in detail about all these activities, and I'm sure you have been hearing during the last few days about them. There has been some demos and presentations. I'll just mention them. If you have any specific question about any of these activities, you can ask me later on, and I will point you to the right person that can help you out. So, activities. First of all, we said we had challenges while setting up these connections. So there are some activities that are looking at automating the provisioning of these services and automating the human interaction while we are setting up the circuits. Imagine how much or how many of these operational costs we could save if all the interaction between our engineers, like, well, my domain have enough capacity, has your domain have enough capacity? I'm using the technology, how do I stitch this technology with your technology? If all this human interaction could be automated. So it's something that Autobahn, for example, is working on. And outside Gen 2, for example, the DCN initiative is an initiative started by Internet 2 that is looking at the same and automating the provisioning of services. What we have to make sure is that all these initiatives are compatible with each other so that this aim of extending the services across different world regions will eventually work. Second challenge, we said, okay, once the service is set up, we really need to maintain the service. So what can we do to ease the fault detection and fault resolution, for example? So there are monitoring activities like PerfSonar, like the end-to-end monitoring, that are looking at this monitoring of multi-domain services. So monitoring that will give you a global view of what is happening in that circuit. But it's not only the monitoring, it's the communication between different stakeholders. And we have some other initiatives that are looking at this communication. We have, for example, the iShare initiative, where protocols and processes are defined to ease that communication between domains. Let's imagine, for example, that I have one database where I store the resources that I use in my domain. And my neighboring domain has a completely different database with completely different structure where she stores the information about their infrastructure. So how can we exchange this information? How can we show an end-to-end information about the resources used across the different domains? So that iShare is defining these protocols and these processes. And you have heard about EduGame many times during this conference as well, as a secure way of accessing these resources by different members of the community. So in the next slide, I will just focus a bit on the monitoring, just to give you some examples. In the part of monitoring and multi-domain monitoring, we look at the monitoring of IP services and the monitoring of Lambda and circuit services. For monitoring IP services, the Jan2 consortium has done is to distribute, implement some hardware and software across Europe. So we have some boxes with some specific software that is being installed in different national research networks and in the Jan2 backbone. And this software enables us to have a full visibility of the network connectivity and the network performance from the IP point of view. This software is able to provide us feedback about well-defined parameters, like the one-way delay or the available bandwidth or the link utilization, not only in one domain, but across all the domains that the circuit is using. This is a snapshot of one of the tools. It's a visualization tool called Persona UI. With this tool, you could, for example, do a trace route to an IP address, and as an output, you could have the available bandwidth, for example, in all the segments across the path, or all the segments that your packet is crossing before reaching the end site. This is another tool, is the one-way delay. And here what we have is information on the one-way delay in different domains. So for example, this one represents different points in Portugal. This one represents different measurement points in Poland. This one represents the interconnection between these countries through the Jan2 backbone. So it's another way of saying, well, I can know what is the delay between two different points in Europe. It could be between, for example, Lisbon and Milan, crossing 3 different domains. While talking about monitoring, of multi-domain monitoring, we said we can look at the IP, but we can look as well at the Lambda services. So let's imagine now that we have 3 different domains. We don't have IP equipment. This is optical equipment and dark fiber. The equipment, you can see they have different colors representing completely different technologies of different vendors. So how can we have a full visibility of what is happening in this connection from A to C? So what the Jan2 consortium has planned, or has done actually, is install some measurement points in each of the domains. So these measurement points will store information about the network elements on that domain. So the network element itself will export information and will say, yes, I'm up or I'm down. So let's imagine that we have a dark fiber cut. Well, all this information is gone to the measurements archives. And we have a correlator tool that will extract the information from each of the measurements archives and will present an end-to-end tool, an end-to-end visualization. So for the first time, these guys here, domain side, could see, okay, so my user does not have a connectivity to the other user located somewhere else in the world because there is a problem in domain A. And this domain C never before may have not had any relationship, any MOU, anything to do with domain A. But not only that, we could say we have a visualization tool, but the options are endless here. We could use, for example, some traps and send these traps to a network operator that could raise a ticket and could send this ticket to the different domains, informing them of what's going on, when, for example, this dark fiber cut is going to be fixed. This is just a snapshot of the visualization tool. You can see here, this is made for the LHC OPN, and this one represents the end-to-end link. We have, for example, the CERN BNL link. That means a link that is going from Switzerland to somewhere in US, crossing different domains. You will see if the link is up and down, and if the link is down, you could say what is the domain that is at fault. So it's a tool that is being offered to the community. It's a tool that is used by the National Research Network, and it's a tool that is being used by projects like the LSCOPN or TEISA. So, okay, so we are getting there. We are putting some efforts in bridging these challenges, but what are others doing on this? Are we the only one thinking that we have a problem to solve? Well, we have the examples of other research networks like Internet2 and ESNet. Together with Jan2, are putting some combined efforts in developing the tools and in deploying these tools that I talked about. For example, Persona is a jointly effort between Jan2, Internet2, and ESNet. But it's not only in the tools. We have to exchange these operational experiences. We need, for example, to have a common definition for services so that the same service has the same name either in Europe or in US, so that we talk about the same when we provide a service to our respective end users. We need to define global operational process. Until now, we had defined operational process for our own domains. Well, we need to align them, and we have to make sure that they are compatible with each other. We have to address our operators' requirements. What is what they need to support these services? And generally speaking, we need to standardize the support that we provide to the users. So this is for the research community. What are others doing? What happened with the ISPs and the carriers and all these guys? What are they doing? Well, I don't know if all of you have heard about IPsphere, but it's supposed to be a forum where ISPs and carriers exchange experiences and information. So I went to the website, and I went to the green paper, and I thought, okay, let's see what they think about all this. And this is just a literal snapshot of their green paper. They say that the network and the services of the future will be created by a diverse set of technologies and an equally diverse set of stakeholders, making the concept of convergence truly multidimensional. So here, the diverse set of stakeholders are our networks, the national research networks, the campus networks. And the concept of convergence and multidimensional is our multi-domain and multi-technology. So it seems that, we have some things in common. They say as well that coordinating complex network technology resources across multiple stakeholders is far more complex than performing the same integration within a single provider. Well, yes, we knew that. That's what all this presentation was about. Having shared resources between different domains make the operational services much more complex. And they say as well that any future business technology framework must address the highest cost, that is operations. And yeah, I think in a different environment than us, but I think we start to see the same type of challenges. And just not to bore you, this is my last slide. So what is the Jan2 vision, where we are, what we want to achieve? Well, we are aware that we are providing more and more complex services, but we are aware that our end users don't care about what our problems are. They want a seamless connection, and that's what we want to provide. We need to bridge all the operational challenges, and that's what we are working on. And we will be leading the market because we are far more advanced than some other environments or NSPs in providing these multi-domain services. The Jan2 project as such will end towards the end of this year, and the Jan3 project will start next year. And the Jan3 project will pursue this objective. We will work towards perfecting the model and enhancing the services that so far have been provided to the end users. And that was the end from my side. I have put some URLs in case you want to know more about this, and I'll be around and available until tomorrow you want to ask me any other questions.
So, are there any questions for Marian? No? No questions? Okay, then thanks, Marian, for showing us what is being implemented in Jean 2 in order to enhance the services for the researchers. Okay, so this is the end. Just to, I think that's the pointer is, okay. Two remarks that we will be very grateful if you can fill the evaluation form that is online on the Terena website. And also to remember you the gala dinner this night. And don't forget a jacket. Okay? So see you there.